would spread the cloths under your feet.
Hi, today we're going to be talking
But I, being poor,
about
have only my
volume
dreams.
integrals,
I have spread my dreams under your
specifically
feet.
volumes of rotation.
Tread softly, because you tread on my
Basically,
dreams.
with the volume of rotation, you're going to be taking some area and revolving it around an axis. Let's say I took this area and revolved it around the x-axis. I would end up with a shape that three-dimensionally looks sort of like this. Now, if instead I were to take that shape and revolve it around the y-axis, I would end up with a shape that sort of looks like this. So it does matter which axis you're rotating it around. You will get a different volume depending upon whether you're revolving around the x-axis, revolving the y-axis, or an axis parallel to these. Now, when you are revolving an area, there are going to be two things that you should initially keep in mind. What is my variable of integration, and what is my am I using disks or washers? So if you have your variable of integration is going to be set by the axis of rotation. If you're rotating parallel to the x-axis, including the x-axis, in other words, a line y equals something, you're going to be using dx. Going back up to this shape, I am revolving this area around the x-axis. I'm going to end up with slices that look like this. The height of that slice, the height of that cylinder, is going to be dx. Now if instead I have rotation parallel to the y-axis, so a line x equals something, including x equals 0, the y-axis itself, I'm going to be using dy. So for this shape, when I revolve this around the y-axis, I end up with slices that look sort of like this. The height of that slice is dy. Now notice that the slices here are solid disks, and the slices here are disks with holes in them, otherwise known as washers. So these are named, the methods we're going to use are going to be disk and washer method. Use disk method whenever there is no gap between the area and the axis of rotation. Going back to this graph, notice there is no, if I'm rotating about the x-axis, there is no gap between the area and the axis of rotation. Therefore, I'm going to use disks. And the way you use disks is your volume is going to be pi some radius squared d some variable, dx or dy. If I use this specific example, let me call this y equals square root of x, and let's say my bounds are from 0 to 4. So if I look at this and just look at the shape, don't worry about the three-dimensional drawing. If you look at the shape, your r is going to be from your axis of rotation to the curve. So that would be my r. Whenever I'm going from y equals 0 to a function, that is always y. And so in this case, I have volume is equal to pi y squared dx, because again, rotating it about the x-axis, parallel to the x-axis, dx. Now, because this is dx, I have to get my volume in terms of only x, so then I would use the fact that y equals square root of x and substitute for y here, substitute my r for whatever my r is in terms of y's, and make them in x's. And as a consequence, I'm using my bounds in x. So because I'm going from 0 to 4, this is going to be a pi integral from 0 to 4, square root of x squared dx. And then I continue. By contrast, what if we have a gap between the axis of rotation and the area of interest? Like we do here. We have this gap here such that when we rotate it, we have a hole in the middle of our shape. We have to use washer method. So if there is a gap between the area and the axis of rotation, we use washer method. The way this works is we have volume is equal to pi, some big R squared minus some little r squared d whatever. Let's look at this shape. Y equals square root of x from 0 to 4 in x. So this is my axis of rotation. My big R goes from the axis of rotation to the far edge of the area. My little r goes from the axis of rotation to the near edge of the area. Now by definition, if I go from y equals 0 to the function, that is going to be x. So my little r is just x. What about my big R? Well, my big R is going from the axis of rotation to this line x equals 4, so that is going to stay 4 over the whole course. So big R is equal to 4. My volume is pi big R squared minus little r squared dy in this case, because we're rotating it about the y-axis, so we use dy. My big R is 4. My little r is x. And because this needs to be in terms of y, I have to make sure it's in terms of y. So I have y equals square root of x. I have to invert that and square both sides to get x equals y squared. And substitute that in. Also, because it's dy, my bound should be in terms of y. So it's going from x equals 0 to x equals 4. When x is 0, y is 0. When x is 4, y is 2. So my bounds are from 0 to 2 in y. Y squared squared is y to the 4th. So now I can integrate. And then calculate. So that's 128 pi over 5, assuming I didn't screw that up. So different volumes, you got different shapes, even though it's the same area. So again, pay attention to whether you're using dx or dy. If it's rotated parallel to the x-axis, use dx. If it's rotated parallel to the y-axis, dy. Note that it's confusing because x equals 3 would be a vertical line, so it's parallel to the y-axis. So don't get hung up on whether it's x equals or y equals. Parallel to the x-axis, horizontal line, use dx. Parallel to the y-axis, vertical line, use dy. And then also pay attention to whether there's a gap between the axis of rotation and the area, or there's no gap. No gap, use dis method. Gap, use washer method. If you have something where it starts out no gap and then ends up with a gap, something like this, then you would have to basically break it up into separate integrals. This part would be disk method, this part would be washer method, with this being big R and this being little r. Okay, all of the examples I've had have only been parallel to the x-axis and y-axis. In the next video I'll cover some involving parallel axis.